This video is about cosets of a subgroup H of a group G and Lagrange's theorem. Suppose we are given G to be a group and H to be a subgroup of G, and we consider two elements A and B in G, and we say that A is related to B if and only if A B inverse belongs to H. We have considered A and B to be in G only, but AB inverse should be in H. If we define such a relation on G, then we are going to have this relation. We are going to prove in this lemma that this relation is an equivalence relation on G. We know already that to verify whether the given group is, the given relation is an equivalence relation, we have to check reflexivity, symmetry, and transitivity. So first we consider reflexivity. That means we need to show that every element is related to itself. How the relation is defined here? A is congruent to B mod H. So if we consider, this is what we need to check. So if this has to be true, then we need to have A B inverse. So in the case of, in this case you have instead of B, A itself. So if we consider A inverse, that is obviously E, and H being a subgroup, it has to be there in H. So since E, which is A inverse, belongs to H, we need to have our A to be related to itself. That is, A is congruent to A mod H, and that proves our reflexivity. Then for symmetry, we shall assume that A is related to B. That means A is congruent to B mod H. So by the definition, we should have AB inverse belonging to H. But because H is a subgroup, inverse of any element should be there in H. So AB inverse, the whole inverse should be in H. But AB inverse, the whole inverse is nothing but B inverse, the whole inverse, A inverse, that is BA inverse. So that belongs to H. So by the definition of this congruence relation, this in turn implies that B is congruent to A mod H, and that proves our reflexivity. So because this one, we will write it as B related to A. So A related to B implies B related to A, that proves the symmetry. Then for transitivity, we assume that A is related to B, that is A is congruent to B modulo H, and B is related to C, that is B is congruent to C mod H. Now the first one implies by the definition of this, AB inverse belongs to H. Here we have mentioned. So by that I should have my AB inverse belonging to H. Then from this you have BC inverse belonging to H. So because H is closed, we should have the combination of these two, that is AB inverse into BC inverse. AB inverse into BC inverse should be there in H by closure. So but B inverse B is E, so A C inverse should be there in H. So that proves that A is congruent to C mod H, or in other words, A is related to C. So whenever A is related to B, B is related to C, that implies A is related to C, and therefore we have transitivity. And because the relation is reflexive, symmetry, and transitive, we have that relation to be an equivalence relation. So we know that once we have an equivalence relation, we can talk about the equivalence class of each and every member of that group G. That's collection. So here that collection being G. So for every element A in G, we can talk about its equivalence class. So by the definition of equivalence class, which is seen already, it is all those elements which are related to A. So by the definition of equivalence class of any element, this is how we have, that is all those elements in G which are related to this particular A. So all those class A, that is equivalence class of A, is those elements in G that are related to A. But remember, this relation is an equivalence relation. So whether I write A related to X or X related to A, it means the same. So here you have X related to all those elements which are related to A. Relation being equivalence, you can rewrite that as A related to X. So, but A related to X, how it is defined? A is congruent to X mod H. And how that congruence is defined? This is how it is defined. So, AX inverse belongs to H. But again, H is a subgroup. So, the inverse of this element should also be there in H. So, you have AX inverse, the whole inverse, and that is nothing but XA inverse belongs to H. So, we have this XA inverse being written as some H in capital H. This XA inverse in H, so we can write that as like this. So again, having got XA inverse to be H, retaining X alone this side, post multiplying both sides by A, what we get is X is equal to HA. So this X is replaced by HA, but my H is ranging over capital H. So you have our class A to be all those elements of this form, and that is denoted as capital HA. That is called right coset of H in G. That is called the right coset of H in G. You're writing the element to the right of H, right coset of H in G. Now, as for the equivalence classes are concerned, we know very well that the properties of equivalence classes, the union of the equivalence classes gives rise to the entire set G. I mean, here it's a group, but generally when we define a relation, we define it on a set only. So, union of all these equivalence classes should be the whole of G. So, but here where this A range over capital G. And we know that each equivalence class is either disjoint with another equivalence class, or those two must be identical. Any two equivalence classes are either disjoint or identical. So we make use of that, and we have these remarks. That is, we have union of all HA, because here class A is nothing but, just now we proved that class A is nothing but our right coset. So union of all right cosets is the entire G, and any two left cosets are right cosets. See, in this case we have got only right cosets, but the same thing can be established for left coset. That will be explained in a short while. So any two right cosets are either disjoint or identical. That is because any two equivalence classes are either identical or disjoint. So based on the equivalence classes property only, we are deriving the properties with regard to right coset. And again, this is known to as A is related to B if and only if class A is equal to class B. So we have A related to B if and only if class A is nothing but HA, class B is nothing but HB. So we have this. So, but how this relation A related to B, how it is defined in this context? It is defined as A is congruent to B mod H. And when do we have A to be congruent to B mod H? If we have AB inverse belongs to H. So this is by the definition. So this says that AB inverse belongs to H if and only if HA is equal to HB. Or in other words, you can also say that HA is equal to HB if and only if AB inverse belongs to H. In very many contexts, we will be using this property. Here in the case of group, that we have HA is equal to HB. But in the case of ring theory, you will have the cosets to be of this form: A plus U, B plus U. So in that case, we will be saying that A minus B belongs to U. And in the same way, in the case of vector space also we have. So this property, we cannot just go away from this property, because it will come in again and again. So if you are thorough with that here itself, then everywhere we can be, what we can say, we can easily use that property and easily understand the concept. So this is what we have. Now we can also define the left coset. So here if G is a group, H is a subgroup, A is congruent to B mod H, written as this. If in this way also we can define. See, what we already defined was AB inverse belongs to H. You can also define this one as A inverse B belongs to H. Then this relation will be an equivalence relation, and the corresponding equivalence class will be left cosets. If we have AB inverse belonging to H, we had right cosets, and here you will have left coset that is denoted as AH of H in G. That is denoted as AH of G. AH of H in, and that is, see, only when you have H to be a subgroup, we can talk about all this. If you have H to be just a subset, we cannot talk about our left coset or right coset. Now, as we said in the case of right coset, the union of all right cosets is the entire G. We have the union of all left cosets to be G. And any two, here we said that any two right cosets are either disjoint or identical. Because we are talking about right coset, here we should have this, and here we are talking about left coset. So we have here any two left cosets. This must be left cosets are either disjoint or identical. And again, A is related to B if and only if AH is equal to BH. The same relation. A is related to B if and only if the class of A is equal to class of B. So here equivalence class of A is left coset, and equivalence class of B is this left coset. So A related to B. And how this relation is defined here? It is defined as A inverse B belonging to H. So as we had here, correspondingly here we have AH equal to BH if and only if A inverse B belongs to H. And if we have G to be an abelian group, there is no need to talk about left coset or right coset. We can have both of them because commutativity holds. So in the case of abelian group, that will not occur. Now, as a consequence of this, we have AH, we can make use of these two. So we have AH is equal to EH, say. Instead of B, suppose we have E, say. Then in that case, AH is equal to H that we will have. And here also, instead of B, if we have A. Sorry, in the case of B, instead of B, you have E, say. Then HA is equal to H. So B is nothing but E. You have taken that to be identity element. So that means A belongs to H you will have. And here also you have B being taken as E. A inverse belongs to H. But once you have A inverse in H, H being a subgroup, you can also say that A belongs to H. So we can club these two, replace our B by E, and have this conclusion AH is equal to H is equal to HA if and only if A belongs to H. Now once you consider E, H being a subgroup, E definitely belongs to H. So we have this being, you can even write this as EH or HE, and both of them will be equal to only H because E is a member of H. But here A is not a member of H. So when A is a member of H, you will have AH to be equal to H is equal to HA. So whenever this is true, my A will be in H. Originally A is considered to be a member of G only. So here if it happens only, you will have your A to belong to H. And whenever A belongs to H, this H will absorb this and you have just H. So these results will be used later quite often. Now if G is finite, then the number of right cosets is finite. So you cannot have G itself is finite. Right cosets, they are determined only by the elements supplied by G only. So if G has finite number of elements, then you should have finite number of right cosets and as well as left cosets. Now So this is obvious. Whenever G is finite, the number of right cosets must be finite. Then the next question will arise: if G is infinite, then should we have for a subgroup of it infinite number of right cosets? The answer is no. For example, if you consider G to be the group of integers under addition and H to be this collection of even numbers, then we can have only two right cosets. One is H itself, the other one is H plus 1. So this one will account for all even numbers and this one will account for odd numbers. The union of them gives rise to G. So we cannot have infinite number of right cosets if G is infinite. Then the possibility is it can even have finite number of right cosets or left cosets. In this case, G is abelian. So either you talk about right or left coset. Now another property of this property between two right cosets is there exists a one-to-one correspondence between two right cosets of H and G. So to prove that there exists a one-to-one correspondence, we need to define a mapping between HA and HB, assuming HA and HB to any two right cosets of H and G. So we consider H to be a subgroup of a group G, and we consider A and B to belong to G. Define a mapping sigma from HA to HB by any element here is of this form only. That is defined in this way, HB. So for every HA in HA, we consider this. Now this sigma is well defined. For well defined, we know that two elements in the domain must be considered to be equal. Two elements in the domain should be considered to be equal, and you'll have to show that the corresponding images are also equal. So we shall consider HA to be equal to some H prime A. We'll consider HA to be some H prime A. So cancelling this A using right cancellation law in that group G, these are elements in G. Remember, any right coset is only a subset, it is not a subgroup. Right coset is not a subgroup, excepting for HE, which is nothing but H itself. You cannot find any structure in this. You don't have actually. So you have this is an equation which is true in G, in which right cancellation law is true. So you have this step. And post multiply both sides by B, so you get this type, but this is nothing but the image of HA under sigma, and this is nothing but image of HB under sigma. Now we just retrace the steps so that we can have sigma to be 1-to-1. That is, for 1-to-1, what do? We'll assume the images to be equal. We need to prove that the pre-images are equal. So images equal means HA, the image of HA under sigma to be equal to image of HB under sigma. Then this is nothing but, the image of this is nothing but HB, and the image of this is nothing but H prime B. Then right cancellation law is true. This is an equation true in G. Using right cancellation law, you have this step. And then post multiplying both sides by A, we get this. So we have got the pre-images to be equal. So it is actually right cancellation law we have used here, and we have got this. So this must be HA is equal to H prime A. We have here HA to be equal to H prime A. So we have to multiply both sides by A only. So you have this. So by retracing the steps, we get sigma to be 1-to-1. Sigma is obviously onto. When do we say that a function is obviously onto? In some cases, we'll be proving actually the mapping is onto. In some cases, we'll use the word it is obvious. Ontoness is obvious. Why? Here, any element in the codomain is of the form HB only, like this only. and that itself is written as the image. So the image set being the whole of the codomain, your sigma should be onto. That is by the definition of onto function. The image set should be the whole of the codomain. Then in that case, your sigma will be onto. So this rule being defined by us, we have shown that that is well defined. Only then it can become a function. Only if it is a function, we can talk about one-to-one, onto, and so on. So you have here, you have proved sigma to be one-to-one, and sigma is obviously onto. So there exists a one-to-one correspondence between any two right cosets of H and G. Now actually, why do we need this? So if only there is a one-to-one correspondence between them, then when we consider HA and HE, HA and HE, you will have, this is a right coset of H and G, this is another right coset. There exists a one-to-one correspondence between these two, which means if I have 10 elements, this one will also have 10 elements. If I have 11 elements here, this will also have 11 elements. So the number of elements here will be same as number of elements here also. So only for that purpose that this lemma is established. So there is a one-to-one correspondence between any two right cosets of H, namely HE and HA in G. So if G is finite, order of HA must be same as order of H. The number of elements in HE, which is same as H, should be same as the number of elements in HA. And here the student should have should bear in your mind that you should not write this. When you write this H right coset, you write like this. You have to write like this and not like this. It's suffix A. This is not the notation to be used. It is like your cow and cough. பசுமாடு கண்ணுக்குட்டி மாதிரி இது இருக்கணும். இது வந்து பிள்ளையாரும் மூஞ்சூர் மாதிரி இருக்கக்கூடாது. So you should have the cough and cow. Okay. So we now move on to Lagrange's theorem. This is our Lagrange's theorem. If G is a finite group, if this word is not mentioned, then the marks for the statement will be cut. If G is a finite group and H is a subgroup of G, then order of H is a divisor of order of G. So if we have G consisting of finite number of elements, then you should have order of H dividing straight line. It should be order of H should divide order of G. When it can happen? When G is a group and H is a subgroup. These two must be given. Only then the number of elements in H will divide the number of elements in G. So that is what we need to establish in this theorem. Now let us consider order of G to be n. Number of elements in G. It's given as finite, so you'll have to consider some number, take it as n. And being subgroup of G, we can have order of H to be R. Now we also know that every group is a subgroup of itself. So in that case, R will be equal to n. So as any number divides itself, we have to have order of H to be a divisor of order of G. We have order of H to be a divisor of order of G. Now suppose R is less than n. Then consider the k distinct right cosets. See, we may have, if we have G consisting of n elements, say E, A1, A2 and so on, say like this that you have, say. Then in that case, it's not that you must have HE, HA1 and so on, so many right cosets. You may or you need not. So suppose I have k distinct. See, if we have for each A1, these are distinct right cosets, then of course I will have n distinct right cosets. But that need not be the case. That need not be the case because when you consider, see, actually here we haven't considered any particular example, but we can say, for example, if we consider G to be S3, which is epsilon, alpha, beta, gamma, delta, theta, then in this case, if we consider H1 to be, say, epsilon alpha, this subgroup, only for a subgroup, right coset or left coset will exist. So we need to compute our left coset or right coset of this. Here we have considered right coset, so we will have H1 epsilon, we have to consider that, H1 alpha we have to consider, H1 beta we have to consider, H1 gamma, H1 delta, H1 theta. So this we have to consider, but this does not mean that there will be 6 distinct right cosets. See, this when you compute, you will have that to be H1 epsilon means epsilon with epsilon. Here you have epsilon with epsilon. So you have epsilon, alpha, epsilon, that is this. And the next one you have alpha. In this place you have, for this you have alpha. So all epsilon alpha is alpha and alpha square is epsilon. So we have these two to be the same. And when you consider the next one, you have, instead of this, you have beta. So what you have is beta, and alpha beta is delta. If we compute, we will know this. Maybe delta, or, depending on how we consider the multiplication. So we can even check it. See, we want to know what is alpha composition beta. So 1, 2, 3. For alpha, 3 is fixed. So 2, 1 that we have. And for beta, we know that 2 is fixed. 2 is fixed. So when you compute this, what is that you get? This is alpha and that is beta. So 1 is taken to 2, 2 is taken to 3. 2 is taken to 2. And here 2 is taken to 1. 1 is taken to, this is alpha we have considered, this is fixed. For beta, this is 3 and this is 1. So 1 is taken to 2, 2 is 2. So we have written that 2 is taken to 1, 1 is taken to 3. And 3 is taken to 3, 3 is taken to 1. So we have this. So cyclically it comes. So this is nothing but delta. So we have alpha beta to be delta. And when you compute this, you will have this to be gamma theta. And when you compute this, you will get it as delta beta. And if you compute this with the table which is given already, you will get this to be theta gamma. So that means even though we have 6 elements in S3, strictly speaking, with each element we have to consider the right cosets. This is how we list the right cosets. But when you compute it, you see that there are repetitions. So that means distinct right cosets only we need to consider. So this one and this one being the same, we count only once. And similarly these two, this one and this one. These two are the same, we'll have to count only once, these two. And similarly, this and this we'll have to count only once. So even though we have 6 elements in G, that is S3, we are having only less number of right cosets. So that is the reason why here we mention that consider the k distinct right cosets, namely HA1 and so on HAK of H in G. Then we know that the right cosets, they behave like our equivalence classes. The union of equivalence classes is the entire G. So you have this this equivalence class is nothing but HA1 and so on. So that is why you have this step. Now when we consider order of G, order of G will be, see, we know this already. Whenever we consider order of A union B, it is nothing but order of A plus order of B minus order of A intersection B. So in this case, there is no element common to them. We have considered only the distinct right cosets. So you will not have A intersection B having any element. So that means this will not come. So which means order of A union B is order of A plus order of B. So that is what we have done here. So it should be order of this. And if you expand it out, this is what you get. But now that we mentioned, just now we mentioned that order of HA is equal to order of H. Order of any right coset is same as order of H whenever G is finite. So how many such order of H that we can write? K times that we have. K such, because HA1 to HAK. So we have K times order of H. So this in turn gives order of H divides order of G. This is what we need to establish. Whenever G is a finite group, H is a subgroup of G, then order of H divides. When you use the symbol divides, the straight line should come. Here it is written with this, so sometimes writing this, putting this straight line may be difficult. But here when you write in pen, in examination, straight line should be drawn to show that something divides something else. So it is not A divided by like this. It is not like this. You have to write. It is the straight line that needs to be drawn. So we are going to have, as a consequence of this Lagrange's theorem, this statement, that is the number of distinct right cosets of H in G. See, we have mentioned here order of G is K times order of H. What was assumed as K? K is nothing but the number of distinct right cosets. So from here we get as a formula, when G is finite, that order of G by order of H is K. What is K? The number of distinct right cosets of H in G. So it is denoted as this, index of H in G. It is index of H in G. So if G is finite, this index of H in G, as a formula you have this. But suppose G is infinite, this is finite, in that case formula. If it is infinite, then you will have to just state only this, the number of distinct right cosets of H in G. So formula can be used when you have G to be finite, and if G is infinite, then this formula cannot be used. You have to use the definition in words given as the number of distinct right cosets of H in G. So all these discussions we have made with the help of right cosets. Remember, the same thing can be done with the help of left cosets also. So we have only in the case of this group, the integers under addition, we have to have only two distinct right cosets. We have one is this, the other one is H plus 1. We have to, we don't have, even though G to be infinite, we don't have infinite number of right cosets. Only there are two, because when you consider, see, for each and every element, here addition is the operation. So for each and every element you can consider the right coset. This is one right coset, this is another right coset, this is another right coset, H plus 3, H minus 1, all these are right cosets, plus of minus 1. All these are right cosets, but when you compute them, actually this will be like 2k plus 2. That's an even number, so that means that will coincide with this even number. And similarly this one will be odd numbers, 2k plus 1. And when you compute this, it will be 2k plus 3, which you can write as 2k plus 2 plus 1. But 2k plus 2 is an even number, say, so 2m plus 1, like that you have. So these two will coincide. So like that, when you enumerate for each and every element of Z under Z, not all of them will be different. So ultimately we will have only two distinct right cosets. One is this, the other one is this. And you have an alternate proof for Lagrange's theorem. See, in this case, you need to establish all these results. Like you need to define on G a relation and prove that relation is an equivalence relation. That gives rise to equivalence class, and by the properties of equivalence class, you have the union, and there exists a one-to-one correspondence between them, and so order of a right coset is same as order of H. So all those have to be proved, and then only you can prove this theorem. If you just write these 3 lines alone for 10 marks question or 20 marks question, full marks will not be given. So right from the definition of that relation till this you have to give the proof. So either that proof you can give, or there is an alternate proof of Lagrange's theorem, and here you know that you don't have to prove those results straight away. You can have the proof of this theorem. So how are we going to prove it? Now we will consider G to be the finite group as before, and H to be a subgroup of G with the order R. Then of course, as discussed earlier, if order of H is also same as order of G, then there is nothing to prove. So we presume that order of H to be a number which is less than the order of G. So that is why it is taken as, say, some number R with these elements in H. So if H is equal to G, there is nothing to prove. Suppose H is not equal to G, then there is an element A in G, but A is not in H. This is bigger one, and this is proper. So we list all the elements so far in 2 rows. So what are the rows? H is H is a subgroup, but A is not in H. If A is in H, then this will be again a member of H only. Then there is no need to list out and there is no need to consider these 2 rows. So A is not in H, that is why we are able to make 2 lists here. So we claim that all the entries in the second row are different from each other, and all the entries in the this we know to be distinct already. These are our distinct elements present in H. That is how we have started the proofs. Let this be the complete list of distinct elements. So these are distinct is known, and this is the new set that we have got. So what we need to prove is these are all distinct, and not only that, you don't have them to be present in the first row. So that means you will have 2 complete set of elements, one with R element, the other one also has R elements. So that is what is mentioned here. We claim that all the entries in the second row are different from each other. These are all distinct. And all the entries in the second row are different from the entries in the first row. There is no common element in these 2. These are distinct, already known. These are distinct claimed here, and these are different from these elements. So all are going to be established. Now if any 2 in the second row, if these 2 are equal, say, that means HIA is equal to HJA with I not equal to J. Then by right cancellation law, we have HI to be equal to HJ. But we know pretty well that the elements in the first row are distinct. So that means we get a contradiction. And therefore the first subdivision holds. That claim holds. Then suppose we have an entry in the second line to be equal to one of the first line. That is, second line elements are like this, so HIA, and first line elements are like this, so you have taken like this, HIA is equal to HI. Or even you can have HIA to be, say, some HJ or HL, something like this. Then retaining this A, see, even here, say, when we introduce this A, we should have also had A not in H means it is obvious that A is not equal to E. Even though that we have not mentioned here, it is understood. If A is E, it will be there in H because H is a subgroup. So it is known already that our A is not equal to E. So if we assume HIA to be equal to HI say, then A will be equal to E. So we consider HIA to be some HJ. So you will have HI inverse HJ. A to be this. And this is in H, this is also in H. H is a subgroup, so closure holds. So you have A to be in H. But we have mentioned already that A does not belong to H. So that means we get a contradiction. Why that contradiction arose? Because we have assumed one of the elements here to be equal to one of the elements over here. So that cannot be true. So all the entries in the second row are different from the entries in the first row. So two sets of elements that we have produced, each having R elements. R denotes order of H. So thus we have listed 2 times order of H elements. If these elements account for all the elements of G, then order of G will be equal to 2 times order of H. So all these elements, they only constitute all the elements of G, means 2 times of order of H will be equal to order of G. So from this, very obviously we have order of H dividing order of G. Now if not, we can find one B in G which is not there in the first line or the second line already mentioned. So now we consider the new list. So these are distinct already known, these are distinct we know already, and there is no repetition in these two. Now that new set that we have considered. So again, what we need to what we need to claim, the elements in this are distinct. The elements in this are distinct, and they are different from the elements here as well as here. So that is what we have to prove. As before, we can easily show that no two entries in the third row are equal to each other, and that entry in the row occurs, none of the entry in this is equal to any of the entry over here. So in the, as we proved in the previous case, we can also prove this case. So if we consider, say for example, suppose there is a repetition, say HI B is equal to HJB. Again, right cancellation law. So you have HI is equal to HJ. But we know that these are all distinct elements. So we get a contradiction. So the elements here are distinct, and they are distinct from this one. If not, as before, HIA is equal to HJB, say. Then what we'll have? We will have that A to be equal to HI inverse HJB. Or you can even say that B, you can also have your B to be, you have B to be pre-multiply, you need to pre-multiply HJ inverse HI. So like this that we have, but B does not take this form at all. So we get again a contradiction. And similarly we can have, so if I have HIB to be equal to HJ, then you will have B to be equal to HI pre-multiply HI inverse HJ. So these are elements in H, so you will have this to be a member, one of the member over here. That is not possible. So because we have assumed B not occurring here as well as here, that is our assumption earlier. So we get a contradiction. That means now we have 3 sets of elements, each having R number of elements. So if these elements account for our G, you will have order of G to be 3 times order of H. So this in turn gives order of H divides order of G. So continuing in this way, when we introduce new element, we produce order of H new elements. Since G is a finite group, we can exhaust all the elements of G. But if only we use K rows to account for all the elements of G, then we will have order of G to be K times order of H. So that in turn tells order of H divides order of G. Now actually the converse of Lagrange's theorem is in general not true. But the converse of Lagrange's theorem is true if you consider G to be a finite cyclic group. If G is a finite cyclic group, then the converse of Lagrange's theorem is true. Now this Lagrange's theorem has 5 corollaries. So that will be discussed in the next video. And remember students that whenever you are asked to prove Lagrange's theorem, either the first proof or the alternate proof that you give, if you are asked to prove the corollaries only, you are supposed to give the proof of corollaries. What the students do is they write along with the theorem all the 5 corollaries. So if only the statement of corollaries are asked, you should not prove them. State and prove Lagrange's theorem means state Lagrange's theorem and give either this proof, this alternate proof, or the other one which involves congruence clauses. That is right coset. So the 5 corollaries, they will be discussed in the next video. Thank you.